everyone, so welcome to today's lecture. So we're looking at vibrations and waves, and to be specific, we'll look at the position, velocity and acceleration as a function of time, and after that we'll look at the motion of a pendulum. So like I said, we'll always be discussing formulas, and then at the end of the topic we'll discuss the auditory sheet, which is going to have practical questions. Alright, so let's quickly begin. Okay, so let's take a look at this diagram here. So look at this diagram, and I'm sure from this diagram, let me just, okay, so from this diagram you can tell to say we have a ball that is moving around this, okay, we have a ball that is moving around this, or it's moving about this point O. It's going round, going this side. So as it is moving, we can see, or rather we can get the projection of this ball. If for instance you have you have a torch somewhere on this side, like an example that we looked at in the previous slide, we can get this projection, rather the shadow of this ball, to be projected there on the x axis. So if we have that, we can come up with a Pythagoras or Pythagorean triangle, or we can come up with a right angle triangle, and then getting theta as this part here. So when you come up with that triangle, let's say we want to find the distance, x from this point to this point. So using SOHCAHTOA, which is just this. So finding this distance x from this point to this point using SOHCAHTOA, and taking into consideration a, which is the distance from a point O to that point there, which is just the amplitude. We're going to call it the amplitude because this is the maximum distance this ball can go. It can't move further than the distance OP. It can't go this side. Yeah, this is the maximum it can go. And if you remember, when you're dealing with harmonic motions, we said, when we looked at the spring, we said when you have a spring like this, the maximum distance it can go from the equilibrium point going this side is called the amplitude. Same applies, the maximum distance it can also go from the equilibrium point going this side is also called the amplitude. So this amplitude is the one that we are also considering this point. So in other words, we're looking at the position, which is just the distance x. So we'll start with finding the position, which is just the distance x, as a function of time. So how do we find that? So we can use what is called SOHCAHTOA, and in this case we're going to use cos, because we have the adjacent and the hypotenuse, which is the amplitude there. So we can find that by saying cos theta, this theta there, is equal to the adjacent over the hypotenuse. So the adjacent is simply just x, and then the hypotenuse is the one that we have as the amplitude. When we cross multiply, we're going to get the value of x being equal to cos theta. So this is what we're going to have as the as the distance x. Now the question is us finding the position, which is x, as a function of time. So how do we do this now? Remember theta, rather when you are dealing with circular motion, under circular motion we know to say finding the arc length, which is given by s, this is just equal to r theta. So this is just equal to r theta. Yeah, so the arc length is just equal to r theta. So we keep this one, we're going to use it somewhere. And then apart from that, we also know when you're dealing with circular motion that when given the distance, the time, you can find the velocity. So the velocity is equal to the distance, which is just the displacement over the time. So in this case, the velocity, since we're dealing with circular motion, the velocity is represented by omega, which is the angular velocity, is equal to displacement. We're going to represent it by x in this case, sorry, not really x but theta. We're going to represent it by theta. When you're dealing with circular motion, displacement is represented by theta, and then over the time. So theta can also be written as omega t. So when you cross multiply, you're going to get omega times t as your theta. So meaning the value of x here, the displacement will therefore be equal to a, while the theta will replace with omega t there. So we're going to have cos omega t. So we've managed to derive the position of this ball in terms of time, or as a function of time. So master this solution here. Master the what is the equation. It's very important. You are going to use it the next time we require it during the tutorial. Okay, so this is what I was just talking about. I was just talking about this, and then after that we simplified that to this. Okay, so let's quickly see how we can find the velocity and acceleration as a function of time. So the reason why I said do not do this topic before we do differentiation and integration, before we do differentiation of trig functions, is because we need to differentiate this for us to get to that, for us to find the velocity. Okay, so how do we now get to that? So let's quickly get this equation here. We have x is equal to a cos wt. So how do we differentiate that? Remember what I said when you're differentiating, if you have y is equal to cos theta, the derivative of this, which is y prime, is simply just equal to negative sine theta. So this is what we're going to use. And then apart from that, we also need to understand that when you have the distance x is equal to, maybe you have 2t squared. When you find the x dt, the x dt is simply just the change in the displacement, or the change in x, which is the distance with respect to time. So the change in x with respect to time is just equal to, so when you find the derivative of this will just be 4t. So this 4t, we know that the change of displacement with respect to time is simply just the same as velocity. So when you find dx dt, the answer that you get is the velocity. Then when you find the second derivative of this, so meaning we have v is equal to dx dt, which are found to be equal to 4t. So to find the other derivative, which is just dv dt, so we're going to differentiate this same expression with respect to t. So this one is called the acceleration. So this one is the second derivative of that. So meaning we're going to find d2x dt2. So d2x dt2 is simply just the acceleration. So dv dt is simply just equal to the acceleration, in other words. So these are very important things to note before we start deriving this. So let us first find the x dt using this expression. So the x dt will simply just be equal to, when you differentiate this a is the amplitude, is a constant, so we leave it like that. And then when you differentiate cos wt, you differentiate the, when using chains rule, you differentiate the value of wt there. So when you differentiate wt, or let me just derive it bit by bit using chains rule. So the first equation that we're going to have here using chains rule is u is equal to wt. And then the second equation that we have is x is equal to a cos, while there's wt we put u. So we find du dt. So du dt will simply just be equal to omega, and then the x dt, the x du will also just be a. When you differentiate cos u, this will be negative sine u. So that is what we're going to have. So according to chains rule, we have the, in this case we're dealing with the x and t. So the x dt, according to chains rule, this will just be the x du times du dt. So when you multiply the two, they are supposed to give you this, because you know that this du and that du cancel. So dx dt will therefore be equal to dx dt will therefore be equal to while there's dx du, we put this expression, which is just negative a sine u. But u, we know that u is simply just wt. This is u. Where did we write that? Oh, it's here. Wt. So we multiply this with du dt. So du dt is simply just omega. So dx dt will therefore just be equal to, when you multiply that, this would be negative omega a sine wt. So this is the one, we remember what I said. I said dx dt is simply just the same as the velocity. So the velocity is just equal to negative wa sine wt. So this is the velocity. So we've derived this one using chain's rule. The same way we've done this is exactly how you get that. So when getting this one, I'm not going to follow the whole procedure. I'll just do it directly. So we have the velocity, which is equal to negative wa sine wt. Let us now find the acceleration. So acceleration is simply just the second derivative of that, or the first derivative of that, which is just dv dt. So dv dt will just be equal to a, and a will therefore be equal to, when you differentiate this, we have negative w there, and then we have also a there. So when you differentiate this, you get w, and then the derivative of sine will simply just be cos wt. So when you multiply all these, you get a is equal to negative w squared a cos wt. So this is the formula for acceleration. This is this is the acceleration of that ball, or rather anything that is undergoing this motion in the as a function of t. So simple as that. You don't have to stress, you don't have to panic when doing that, or you don't even have to start remembering, you just derive them. Alright, so let's quickly move on to the next question, or rather the next slide. Okay, so the other thing that we need to note is that the angular velocity is equal to the change in displacement over the change in time. That is the angular velocity, the change in time. So the change in displacement, when, for instance, this ball that we had, this one which was rotating, going this side, if it makes a complete revolution, we're going to have a complete revolution is equal to 2 pi. In other, in degrees, it's just 360 degrees. So we just put 2 pi there. Then everything divided by the time taken to complete one revolution is just the period. So 2 pi over t is another formula for the angular velocity. So now remember what we discussed in the previous slide, that frequency is just 1 over t. So this one can also be written as 2 pi times 1 over t. So while there is 1 over t, you can just replace with frequency. So the angular velocity will now just be equal to 2 pi f. So it can also be written as 2 pi f. So this is another important formula that you need to know. So now, while there is while there's angular velocity in those formulas that we found, let me just write them. So in other words, we found that the angular velocity can be written as 2 pi f. So if 2 pi f is the angular velocity, remember we had x is equal to a cos wt. So while there's w there, we can just replace with that. So the value of x as a function of t can also be written as a, this is the position, which is a cos, where there's wt, we can just put 2 pi f, and then we also include the t. So this is the first formula. The second formula was the formula for velocity, which was just negative a omega sine. So what is Wt, we put 2 pi ft. Then we also have the formula for acceleration, which is also equal to negative a omega squared, and then we have cos 2 pi ft. So these are also important formulas to note. You need to know them. Alright, so let's quickly move on to the pendulum, the motion of a pendulum. Yeah, the motion of a pendulum is also one of the important topics that we need to cover. So I've talked about this, I've talked about all these formulas. So the motion of a pendulum. So the motion of a pendulum, imagine you have a pendulum like this, and as you can see, let me just draw this part there. We have something like this. Then this is what is the weight of the bob. This is the weight of the bob. So the weight of the bob given by mg. Then you have the direction of the tangential force. Yeah, so the tangential force in this case will just be given by mg. It's just the x component of the weight of, or rather the force, the force of the bob. We also have the tension this side. Okay, so the tangential force, which is just Ft, will just be given by negative mg sine theta. Why negative? Because it's facing down. If you take up as positive. Okay, so that is the tangential force. So from there, we can also derive some formulas. Remember what I told you to say. The arc length, which is just s. This one is just given by r theta according to circular motion. So we make theta the subject. We can have theta is equal to r. So we're going to divide by r, divide by r. So it's going to be s over r. So in this case, the value of r, which is the radius, is being represented by L. So theta can also be written as S over L. So meaning on this part there, where is theta, we can replace with S over L. Hence, we'll have something like this. So the tangential force is simply just equal to negative mg sine S over L. So this is what we're going to have. So you need to master all these formulas. You need to know how to derive them rather. Okay. So now when you are dealing with a pendulum, we always consider that this theta here is a very small theta. So when you take into consideration the thetas to be less than 15 degrees, when you find let's say when you find theta in radians, when you find theta in radians, you have let's say for instance, if you have 10 degrees, if you have 10 degrees in radians, 10 degrees in radians, when you use a calculator, okay, when you use a calculator, 10 degrees, this is just the same as, in radians, this is just the same as 0.17, when you round it off, 0.175 radians. And then when you find sine 10 degrees, sine 10 degrees, this is also going to give you something similar to that, which is just 0.174. So when you look at these two numbers, they are approximately equal. So in other words, we can make a conclusion to say we can make a conclusion to say 10 degrees in radians is equivalent to sine 10 degrees. So in other words, 10 degrees in radians, this should be converted to radians, is equivalent to 10 degrees, sine 10 degrees. Therefore, all the angles that are less than 15 degrees, if you are using such angles, you can therefore conclude that the F that we found, the tangential force, which was just equal to negative mg g sine theta. So this force, while there's this part here, while there's sine theta, we can just replace with theta, because we said theta in degrees, theta in radians. This is what we said. We said theta in radians is just equivalent to sine theta in degrees. So this is the conclusion that we made. Hence, while there's sine theta there, we can just put theta in radians. So if you're dealing with theta in radians, we can just say theta, the tangential force is equal to negative mg. While there's sine theta, we just put theta. Of course, this theta is supposed to be in radians. So remember what we said. We said theta can also be written as S over L. So while there's theta there, we can put S over L. So we're going to have negative mg S over L. And then this can be written as negative mg over L times what? Times S. So these are some of the formulas that you need to put into consideration. You need to know them by heart. And as a result, so we also have to recall, if you remember very well, we also talked about the angular velocity, that we said this can be written as 2 pi f, which we concluded in the previous lesson that we had, that it can also be written as k over m, the square root of k over m. So now, remember, we when you combine this force with the harmonic motion force, the one that we talked about using Hooke's law, we said this force can also be written as, so this Ft can also be written as negative k x, negative ks, which is the arc length. So negative ks, so when you combine this expression and this expression, s and s will cancel. Okay, let me just write it properly so that you see what I'm talking about. So I'll write it here. So let me demarcate. So I said when you combine this one and this one, we're going to have, while there's ft, you put negative k s, and then you have this other part, which is negative mg over L times what? Times s. So this s and that s will cancel, this negative and that negative will cancel, meaning the value of k will just remain as mg over L. So while there is k in this expression, while there is k, we're going to write mg over L. So this can also be written as the square root of mg over L, and of course divided by m. So this m and that m will cancel, so we'll just remain with in other words, the angular velocity can also be written as so when this m and that m cancels, this can also just be written as g over L. That is the angular velocity. Yeah, so that is the angular velocity. You can also write it as g over L. So from this, just from looking at this expression here, we can make a conclusion that the angular velocity of a pendulum does not it does not depend on the mass of the bulb. So the angular velocity of a pendulum does not depend on the mass of the bulb. So we can also get another formula, which is the formula for period. We know to say, okay, let me just write, let me just erase everything. We know to say frequency is equal to 1 over period. 1 over period, meaning the period can also be written as 1 over the frequency. But remember, the angular velocity, or rather, let's say the frequency here can also be found. The frequency here, we found frequency to be okay. Let me write the formula first. Let me write the formula. Said angular velocity is equal to 2 pi f. 2 pi f. So meaning the frequency there can also be written as the angular velocity over 2 pi. That is the frequency. So if we were to write this if you want, we can replace this there. So the period will simply just be equal to 1 over, we divide by W over 2 pi. So when we divide that, this will simply just be 2 pi over W. But remember, W, we said this is just equal to the square root of G over L. This is what we found as W. So from there we can just say the period is equal to 2 pi times what? Or rather over, let me just write it properly. So this is just the same as 2 pi over the square root of G over L. So when you divide this, and you want to take it on top, it means that what is under the root there will switch. So we're just going to have the period being equal to 2 pi times the root of L over G. So even the period does not depend on the mass of the bulb. So the time taken for the bulb to complete one cycle does not depend on the mass. All right. So this is the end of today's lecture. Let us make sure that we are mastering all these formulas that I'm deriving, so that it won't be difficult for us to be solving the questions from the tutorial sheet. All right. So this is what I was just talking about. I've talked about all this. I've talked about everything here. All right. See you in the next. Lecture that we're going to have. My name is Harmtedy. Shalom, shalom.